Welcome Chemistry 12-2. Here's a very short video to review the outcomes that we have ticked off while we were working through the equilibrium unit. The acid-base unit that we're moving towards, which we'll be working on in weeks 5, 6, and 7, it's very intertwined, it's very closely related to our concept of equilibrium. So I wanted to make sure that you were okay with some highlights before we moved forward, and here's a short video to discuss them. The first thing we need to talk about is the collision reaction theory. And the collision reaction theory was really important because it talks about the success of collisions or reactions. So if we want to have a successful collision and we want our particles to collide and rearrange and create a new product, we need to think about or check off two key boxes. Do we have sufficient energy? Here, the symbol capital E, little a is activation energy. If you recall, activation energy is the minimum amount of energy that particles need in order to collide and rearrange if they're in the proper orientation. And when they rearrange, they make a new product. And so every reaction's a little different, and we drew some pictures. So this is kind of the hill that the particles, the energy has to get up past that hill so that they have sufficient energy and proper orientation, and then they can rearrange and create new products. So we need to have successful collisions. Often particles will collide, but without these two things, and so therefore the collision is unsuccessful. In order to create product, you need successful collisions. So you need sufficient energy and proper orientation so that they will rearrange to create product. So we looked at the rate, how quickly can reactants rearrange to create product. And there's a couple ways you can quantitatively look at this. You can put a number on it. So if we want to find the rate of reaction, you can take a look at the amount of product formed over time. So how quickly are you producing your product? So you can measure your product and how long it took to produce it. Or you can look still at the forward reaction, but how quickly did the reactants disappear and how quick did that occur? So by a function of time, you can take a look at how quickly your reactants are disappearing or how quickly your products are forming. And that will give you the reaction rate for your reaction. Now, we also looked at some different ways to increase this reaction rate. So what are some things we can do to make our reaction rate increase or go faster? So what factors can we change? The first one is concentration. So if you increase the concentration of your chemicals or your reactants, right, probability-wise of them being successful is higher. The more chemicals we have colliding, the more collisions are going to be successful because they reach that minimum activation energy and they have proper orientation so that they can rearrange into products. So increasing the concentration allows for more collisions, and therefore more collisions are successful. Same thing with temperature. If you increase the temperature, you're messing with that energy, right? Collisions can reach that minimum activation energy if they have an increase in temp, because the temperature gives them more kinetic energy. So temperature, remember, is just a measure of the average kinetic energy of particles. So if you increase the temperature, you're increasing the kinetic energy that these particles have. Therefore, they have more activation energy, and we can have more successful collisions. That's the bottom line. What can we do to have more successful collisions? That's what's going to increase your rate. We can take a look at a catalyst. We now know that a catalyst is a chemical that can be used over and over again. It's not consumed in the reaction. But what a catalyst does is, again, it's working with this minimum energy. It doesn't give the particles more energy. It actually reduces the amount of activation energy necessary for the collision to be successful. So it brings that hill down. It reduces that minimum activation energy for the particles to have a successful collision. They won't need to have as much kinetic energy. And finally, you can take a look at pressure. If you're dealing with gases, when we talk about solids and liquids, those particles are so close together, changing the pressure does not affect them. But remember, gases, the particles of gases are very, very far apart. There's a lot of empty space. So if we start changing the pressure, we can cause these particles to move further apart or closer together. And so increasing the pressure of gases is just like increasing the concentration of gases. If we increase the pressure, we bring these gas particles closer together, Therefore, they can collide more often. More collisions, more successful collisions. So those are a few things you can use in order to increase the reaction rate of a chemical reaction. The next thing we looked at, and actually I'm going to flip over here quickly. The next thing we looked at is dynamic equilibrium. And with dynamic equilibrium, there's a couple things to remember. Dynamic means it's always going on, nothing ever stops, but there is a balance that is reached. And when that balance is reached, what is equal? Something's always equal in a balance. And when we look at, there's different types of dynamic equilibrium, but when we look at chemical equilibrium, we know it's the rate of the reactions. That's what's equal. So the forward reaction is moving as quickly as the reverse reaction. I should maybe talk about that. Up until this unit, we thought that there was always just a forward reaction. Reactants were rearranging to create product. What we found here now is that there's also a reverse reaction happening. And a reverse reaction is when the products break apart to reform the reactants. And so that forward reaction gets things started, but that reverse reaction kicks in eventually. It can kick in really late or it can kick in really early. This is a misconception that a lot of people have. When we have equilibrium, a lot of people think it means we have equal amounts of reactants and products, and that is not true. It's not necessarily true. It's the rate that's equal. So when the forward reaction is happening as fast as the reverse reaction, that's when we have equilibrium. So as we make one new product, that product breaks down and makes one new reactant. We make one new product, that product breaks down and makes one new reactant. So that is when we have equilibrium. And that's when the concentrations stay constant, but they're not necessarily equal to each other. We looked quantitatively, so how can we put some numbers on this? If this is our equation, we can come up with a KEQ expression or KEQ law. We put our products on the top and our reactants on the bottom. This is going to be key. We talked about KW, but in our new unit, we'll talk about KA and KB. So they're all equilibrium constants, basically of specific types of reactions, okay? So products on the top, reactants on the bottom. You can see your coefficients become exponents. I put this here to remind you, it's always just your aqueous compounds and your gaseous compounds or gaseous compounds. It's not solid or liquid again. Solid and liquid particles do not affect the equilibrium. The other thing we looked at is a benchmark. So for KEQ, if it's greater than 1 or less than 1, that tells us something about the equilibrium. When KEQ is greater than 1, it tells us that products are favored. When the products are favored, it means we've made a lot of product. So if you think about that, in order for us to make a lot of product, that forward reaction, that's what makes product, it happened or it was going on for quite a while before the reverse kicked in. So we say it's reached late. Equilibrium was reached late. Equilibrium is, when that reverse one kicks in and becomes equal, that's when equilibrium is reached. If your KEQ is less than 1, it means that your reactants are favored. So you had a heck of a lot of reactants and not much product made. And therefore, the reverse reaction kicked in really early. So we say it was reached early. If you have a KEQ, here it is numerically, we can plug in our concentrations and we can come up with a number. This one is quite a bit larger than or greater than 1, so we have our products favored. There's another way we could take a look at KEQ, describing when the equilibrium is reached, so the position of equilibrium, and that is percent reaction or percent yield. Percent reaction or percent yield, it's a numerical value. In this case, it's 11%. We write it right over the arrows. These are reversible reaction arrows because there's one going forward and one going backwards. And here we have a percent reaction of 11%. And that's quite tiny, right? Thinking about 100% is the best. So 11% is quite tiny. What that's telling me is that these guys are, when they have sufficient energy and proper orientation, they're rearranging into this guy. But unfortunately, only 11% of all that they could create was occurred before the reverse reaction kicked in. So that's what this 11%. They were only able to make 11% of what they should have been able to make before that reverse reaction kicked in and they reached this balance. Because once they reach a balance, no more product or reactant is created, right? Their concentrations stay constant. So they were able to create 11% of the amount, the ideal amount, and then the reverse kicked in. so this is a low percent yield. We would say here that the reactants are favored. So our benchmark here is 50%. So if it's less than 50%, reactants are favored. If it's greater than 50%, products are favored. Okay? I'm just going to switch back before I go to pH. If we jump back here, I should have put this in a better order. Le Chatelier's principle is the next concept that we looked at. And this is talking about if your equilibrium is, if there's a stress put on your equilibrium, and different stresses can be, what if you change the concentration of some of your products or your reactants? How will that affect your balance or your equilibrium? What if you increase or decrease the temperature of a system that's in equilibrium? That's going to change your equilibrium. What if you change the pressure, especially if you have gas compounds in your equilibrium expressions? How is that going to change? So the rule, Le Chatelier's principle, basically says if there's a stress applied to a dynamic equilibrium, the system changes in a way to relieve that stress. So we talked about it as fixing itself. So when there's a stress put on a reaction that's in equilibrium, the reaction will do the opposite in order to fix that stress and to regain a new balance. So you can look at these at your leisure. Essentially, you got to think about, does the does the forward reaction have to speed up to fix this, or does the reverse reaction have to speed up? If it's the forward reaction that speeds up, we say it shifts right. And I'm having a hard time finding a cursor here, so bear with me. Right? Okay, so it shifts right if the forward reaction is speeding up, and we say it shifts left if the reverse reaction is speeding up. And when the one thing I always remember when I'm working with Le Chatelier's principle, in a forward reaction, your products are being used up and they're making more, your reactants are being used up and they're making more product. In a reverse reaction, your products are being used up and they're making more reactants. So be aware of that. With temperature, we think of energy as one of our reactants or one of our products. If it's endothermic, energy is on the reactant side, and if it's exothermic, energy is on the product side. So it's the same idea. If you increase the temp, the system wants to decrease the temp. So if it's exothermic, the system will shift left to decrease that extra energy. If it's endothermic, the reaction would shift right to decrease that extra energy. And pressure, it's all about how many gas molecules you have. So if you increase the pressure, the equilibrium wants to shift to the side of the reaction that has less gas molecules. If you decrease the pressure, the system wants to do the opposite, increase, so they'll shift to the direction that has the higher number of gas particles. Okay? And the last thing I want to talk about is this idea of Kw. So this was kind of our last week. Kw, which is the ion product constant for water. I know this is a busy slide. So Kw, the ion product constant for water, we know that we have the H positive and the OH negative. And the H positive and the OH negative, when we multiply them together, we get Kw. And Kw is a constant for us. Kw is 1.0 times 10 to the negative 14. And 1.0 times 10 to the negative 14 at 25 degrees Celsius will always stay that amount. And if you take a look, we use the concentration of these guys in order to think about what type of a solution we have. So if you measure the amount of H positive and OH negative, we can come up with what solution we've got. So when they're equal, and I think you guys will agree, when they're equal, we have a neutral solution, right? And a neutral solution will be pure water is a great example of a neutral solution. Well, what happens if you have your OH starts to drop, okay? But the Kw has to stay the same. So it's like a teeter-totter. If the OH starts to drop, the H plus has to increase to maintain this constant Kw. And in that case, what happens is we don't have a neutral solution anymore. We have more H positives and less OHs. So we have an acidic solution. Okay, so comparing these amounts will give you a quick way of talking about or describing the solution you're talking about. So what happens if the opposite occurs and we have a increase in OH and a decrease in H plus? Okay, and in that case, again, it's that teeter-totter, right? If the OH goes up, the H plus has to go down, and we have a basic solution. So we can use these concentrations to help us out. We also practice with our calculator, and we know Soren Sorensen said these numbers are kind of tiny and hard to work with, so he came up with a pH scale. So we can find the pH of any solution if we know the H3O concentration, and we can find the pOH as well if we knew the OH concentration. Pretty important to match those up. And we can also take these two and add them together. They add together to be 14. All right, one last note to share with you before I finish, and that is, don't forget H positive, H3O positive, and proton mean exactly the same thing. They're all the same thing. So the hydrogen ion, the hydronium ion, or even a proton, in the next unit, we'll be using these kind of interchangeably, so be aware of that. Okay, so this was a quick, I don't know how quick, let's check our time. It was somewhat quick, and it was a nice review of equilibrium. What you'll find late next week, I am going to post an equilibrium unit review. Okay, it's a self-check. You don't have to pass it in, but it's really, really important for you guys to try it. All of you guys are here because you want to learn a little more chemistry before we move on to first year university, or AP chemistry for some of you. And so you want to make sure that you are getting this and it's making sense. So the self-check is for your use only. There's going to be 18 multiple choice questions, okay? I'll post it later on this week, and I'll put it in the post section, not in the assignment section. What I want you to do with it is I really want you to be true to yourself and answer each of the questions in your notebook. Do it alone and before checking answers, okay? You want to make sure you know for your benefit how well you did on this assignment. I'll post the answers later next week. And actually, Mrs. Tate used the same assignment, and she's going to create a video explaining each of the questions. So you'll get a chance to go back, correct your work, and see where you went wrong. But I think it's important for you to do a self-check right now. We're at the end of the unit for equilibrium, and you do this, and hopefully you do well. And you can let me know how you made out. Okay? Thank you for your attention. I'll talk to you soon.